So hello everyone, this is lecture 38 for the mathematical physics. In the last lecture we were discussing about the functions, some special functions in the complex domain. Okay, means like exponential function, log function. Okay, so we were talking about the logarithmic functions, and we already proved that how we find the log of a complex number, and we were discussing some different cases. So first we were discussed this. When it is real and positive, then it will give you the simple single value function. It will be a real natural logarithmic, same as it. Okay, now let's say z is real and negative. So in complex domain, we also can find the log of negatives because we know in the formula of log z, where z is complex, we have modulus of z. So if it will be negative, so again it will come to be positive. That's why we can find the log of z negative also in here. So if z is real and negative, then it will be simply log z plus iota pi. Okay, so how you can see that? See, if z is negative and real, then if you see in the complex plane, this negative will always lie in this x-axis on the negative side. So this argument will always be pi. That's why I write this principal value of log z as log mod z plus iota pi. Okay, now see, this can have infinitely many values because this is our principal value. When you need to find all the values, you will use this formula. Ln z will be this principal value plus 2n pi iota. So by putting n equal to 0, 1, 2, 3, 4, 5, you can get all the values. For n equal to 0, you will get the principal value. So we find the principal value for our negative, means real and negative. So this will be your value. Now let's see some examples. Let's say we have z equal to 1. So for z equal to 1, how you will find the principal value? It will be again log of mod z will give us 1 again, plus the argument of 1 will be, it will be on the positive side of x-axis, so it will be argument will be 0. So I argument is 0. So you will get log 1 and log 1 is 0 again. So see, it is, if it is real, okay, then you will have the simple same log as it is 0 for this and 0 for this. Here also when you write all the values, then you will get this, the principal value plus minus 2n pi iota. So all the values will be these, means imaginary. There will be no real value because if the log of this in the real plane is 0, that's why we will get all the imaginary values here. See, using this formula you can find all the infinite values. So in complex plane you have infinite values of log. Remember this. Okay, in the complex plane, log function has infinitely many values, and you can find the correlation between the real and the imaginary. That real part is 0 because this is real, so real of log is always 0. That's why we are getting 0 in the real axis, but all the imaginary axes are infinite. Okay, now let's see for the z equal to -1, that is negative. So we know for this argument will be pi because it will be on the minus side of the x-axis, and mod of this will give you 1, and log 1 is 0 again, and I pi iota will be your principal value. Then principal value plus 2n pi iota will give you infinitely many values by putting n equal to 0, 1, 2, 3, 4. So you will see by replacing the signs you will get all these values plus minus iota pi plus minus 3 pi iota I, and all these values will be your value of z equal to -1. See, these are also imaginary because in the real axis the negative of log is doesn't exist. Okay, that's why you are getting all the imaginary values. Now let's see for the z equal to iota. So log of iota will be, means first find the principal value. So mod of this is nothing but that will be 1 again, and iota is lying on the y-axis, so argument of I is pi by 2. So this will be your, this is 0, and this will be your principal value. Now log will be principal value plus minus 2n pi iota. So these will be your infinitely many values of log in the complex plane. Now let's see some complex example. If log of 3 minus 4 iota, we need to find the log of this. So what will be this? First principal value. For principal value, log of 3 means log mod of this 3 minus 4 iota plus iota, then argument of this function. So you can find the argument of any complex functions or complex number. I already told you how to find that. Okay, just see in which plane they are lying. So it will be -4 in the y and 3 in the plus. So it will lie in the fourth quadrant. Okay, So in fourth quadrant, then it will be your negative, the argument will be negative, and tan inverse y over x will give you the value. So it is in radian. So that's how you can find. And also the modulus of this under root 3 square plus 4 square will give you log 5. Log 5 is equal to this. So that's how you can find the values. So this is your principal value. Now log of this will be principal value of 3 minus 4 iota plus minus 2 and pi iota. So you just need to remember this formula only, then you can solve any kind of log function complex number. So these are your values. Now see, we know in the real plane we have this formula, exponential log x equal to x. So it is valid in the complex plane also. Exponential log z is always z. Okay, so we can verify this formula. We know log z is nothing but log r plus iota theta. We already proved this, means in the previous lecture, where it was z equal to r exponential I theta. So that's how you can get this. So now log z can be written as this, log r plus I theta. Now exponential log r and iota theta can be, exponential iota theta can be written as cos theta plus I sin theta. Now this is our real, this r is real value, so exponential log r will be r, and this is again z. So that's how we prove that exponential log z is equal to z. Now remember this result, very important. Now let's see how to find the, means we need to find this log of exponential z. So this is very important result. This is z plus minus 2 and pi iota. So let's prove this. To find this log exponential z, we need to use the formula again. First find the principal value, then plus minus 2 and pi iota. So principal value of this is nothing but log of mod of this exponential z plus iota, argument of exponential z. Argument of exponential z is, we already proved in the previous lecture, that is y plus minus 2 and pi. Okay, and we already find it, this means the property of exponential functions, that mod of exponential z is exponential x, the real part, plus iy, this is our principal value, plus minus 2 and pi iota. So for n equal to 0, you will get argument of exponential z as y. So this is your principal value. Now log of exponential x is nothing but x. This is z and plus minus 2 and pi iota. So this is same as this. So that's how you can prove this. So remember this result, very important. Now as we have seen already many functions, and now let's see general power, means if z is z to the power c, means if there is complex power of z, you get sometimes iota powers to iota, iota power 3 plus 4 iota. So how to solve these kinds of functions or these kinds of numbers? Okay, so let's say z equal to x plus iota y, and z to the power c, c is complex, denoting complex. So it can be written as exponential c log z. It can be written like this because c will go to the power of zc, and exponential log z, c will give you zc. So just remember this formula, this will be very helpful in all the questions of this type. So in general, c is complex, z is not equal to 0. So c can be anything. If c is this simply number 1 2 3 4 and all, then zc will be single valued, means there will be single value functions. We already talked about this. And if c is minus 1 minus 2 minus 3 minus 4, then we know these are the nth roots. We already talked about this, how to find these nth root. But now is there is third case, means c is some complex, means 3 plus 4 iota 3 iota, means that kind of situation. How to solve that kind of situation or question? So let's say zc equal to n, this z means this is a third. Okay, so z to the power 1 upon n can be represented by this form. So we can write this form exponential 1 upon n log z, because this will be in the power of z to the power 1 upon n, and then it will be again z to the power 1 upon n. So these can be written like this. So remember this came from here. So this is a very important result. This is nth valued. Now if c is complex, means if this c is complex, means this is some iota form, then this z to the power c have infinitely many values. Because we remember from here, if n is minus 1 minus 2 minus 3, means it's a third and of z and nth root, then we are getting a fixed number of values for depending on the what is n. Okay, and if it is 1 2 3 4, then it will be single valued. But if c is complex, then we will have infinitely many values. Let's see one example. Find principal value of iota power iota. So how to solve this? So you just need to remember this formula. So iota power iota can be written as exponential iota log iota, because this will go to the power of this and it is again iota power iota. Now you need to solve this log iota. So log iota you can solve using this formula. Means first find the principal value, then plus minus 2n pi iota. So log iota, principal value of this will be what? Mod of iota will be 0, means mod of 1, log 1 will be 0, and argument of iota is nothing but pi by 2. So it can be written as exponential iota, means this, and then it can be written as exponential log iota. So means it's like exponential, then inside it is I log I. So I log I can be written as, this is our principal value, because mod of iota is 1, so log 1 will be 0, plus iota, argument is pi by 2, plus minus 2n pi iota. So we just solve this log iota and written is here, and multiply with iota, and this whole thing is in exponential. Okay, now to find the principal value of iota power iota, you need to put n equal to 0 here. So what you will get, I square pi by 2, this will give you minus pi by 2. So for n equal to 0, this iota power iota will be exponential minus pi by 2. So that's how you can find the values. Let's see some more example. Find principal value of 1 plus iota raised to power 2 minus iota. So this will also have infinitely many values. So let's see, but we need to find the principal value. So 1 plus iota 2 minus iota can be written as exponential 2 minus iota log 1 plus iota. Now exponential, and inside it is this function. So find the value of log 1 plus iota using the same formula, principal value plus minus 2n pi iota. So principal value of log 1 plus iota will be, mod of this will be root 2, and argument will be pi by 4. So this is our principal value plus minus 2n pi iota. Now multiply this whole term with 2 minus iota and exponential outside. So we get this form. Now we will multiply this inside. So 2 log root 2 will become here, and when we multiply this minus iota, take the iota common from these two, then I square will give you minus 1, multiply minus will give you 1. So it will give you exponential this whole term. Now inside it will be remaining, means 2 multiply with these two, pi by 2 it will given, and 4 and pi and iota will be taken common, then minus iota multiply with this. So you will get this form. Just simply I just reduce this form to this form. You can check this. Okay, so we get this. Now for principal value you need to put n equal to 0. For n equal to 0 it will be exponential pi by 4, and this will go on inside, so it will give you e log 2, so it will be 2 again. So 2 exponential pi by 4. Here for n equal to 0 you will get minus log 2 root 2 plus, now this is exponential I theta, so it can be written as cos theta plus I sin theta. So this will be your answer. Now this is nothing but cos 90 minus theta, so it will give you sin theta, this will again sin theta, and this is nothing but sin 90 minus theta. Sin 90 minus theta will give you cos theta. So this will be your principal value for this 1 plus iota raised to power 2 minus iota. So these kind of questions are asked in the examinations. You must make sure that you understand this thing properly. Okay, now we will move forward. Here we ended this all complex numbers and their differentiation and all, but now we will start with the integration, means how to find the integrals of complex numbers. So we will start with contour integrals. See, in the real numbers we have only single axis integration, and that's why we call it as single line axis or the line integrals. But here in complex plane we have a point, or in the complex plane means it is made up of two numbers, that is one is real and one is imaginary. So now the path or anything which we need to be integrate formed by this complex numbers will be called contour integral, because this is forming a contour. So the integral of a complex variable over a path in complex plane known as contour integral, that is path contour. Okay, so we call this integral as contour integral in the complex plane. Okay, so let's say we need to find the integration from z0 to zn. Then let's divide this whole contour into the n minus 1 parts. Okay, means there are n minus 1 points inside. So let's divide the path into n intervals by taking n minus 1 intermediate points. So these are n minus 1 points, and there are more this. For comfort, let's call it E. So we divide this Z0 to Zn in the n minus 1 parts inside. Now in each part we have E1, E2, E3 and this kind of terms. Okay. So between Z0 and Z1 we have E1, between Z1 and Z2 we have E2, and between Z2 and Z3 we have E3. So let us divide the path into n interval by taking n minus 1 intermediate points up to Z1 to Zn minus 1 from Z0 to Zn. Now consider the sum Sn. So this is our integration sum actually. Means Z will be going from 1 to n. Now f, ej and zj minus zj minus 1. So this is like means now you put z equal to 1, you will get z1 minus z0 and will lying between them, so it will be e1. So here as simple, then again for z equal to j equal to 2, you will get z2 minus z1 and then e2, same will go on, and this will give you the integration of this contour. Okay, now if n tends to infinity, means this difference is very small between z2 and z1 or anything, so we will write it as dz, and when n tends to infinity, this difference is tending to 0 for all, then we call it as integration, where ez is the point between zj and zj minus 1. So this will tends to 0 for all. If limit n tends to infinity, Sn exists then. So then how we can write this when this is infinitely many, means this difference is very small. So limit n tends to infinity, sigma z equal to 1 to infinity. Now we are summing up just in the integration we do. So fe zj minus zg minus 1. So it will go from z0 to zn, fz and dz. So this is fz because at any point this is a point. So fz dz. Now this is a contour integral, so we denote it by the c. So we write c here, this denotes the contour integral, so fz dz. So we can write this in the form of this. So this is just a definition of contour integral. That's how you come to this expression of integration of complex numbers. Okay, now let's say fz equal to, means we know we can write this fz in the form of u and v. U is the function of xy and v is the function of xy, and where z is nothing but x plus iota y. So dz will be dx and iota dy. So what is fz dz? So we have fz, we have dz. Let's just multiply them. So it will be u dx and I u dy. So just separate the imaginary terms and the real terms. Again multiply this. So it will be iota v dx and iota square will give you minus. So minus v dy. So you will get the separate real term and the imaginary terms. Okay. So fz dz will be this. Now we need to integrate this from z1 to z2. This is called the complex integration. So let's say we have this any contour and we need to integrate from z1 to z2. At z1 we have x1 y1, at z2 we have x2 y2. Okay, so it will go like this, means integration fz dz will be this. So we will differentiate it separately, means integration of this will give you integration of this and integration of this. Okay, and limits will be x1 y1 to x2 y2, and here you will get dy dx dy, here you will get dx dy. So this is the form, this plus this. Okay, this is again the same, and this is called the complex sum of real integrals. Okay, because now what we did actually, we just converted this complex integration into the real integrals, means now with the help of real integral forms we can calculate the complex integral. That's what we did here. Now it can be closed contours or the open contours. So here what we were discussing, it was the open contour from one point to another, but it can be closed also, means like this, closed contours can be also be there. So we represent this closed contours by this, and this is the closed contour sign C. And here definitely in the question direction of the contour will be given. If it is in the anti-clockwise direction, then it will be represented by plus the integration, and if it is in the clockwise direction, it will be represented by minus. Then you will use the negative sign. So it just came from there. When theta to this direction is positive always, that's why the rotation is positive, consider this side, and rotation this side will be negative. So this is the definition of closed contour. Integration is simply this. Now let's see the Cauchy integral theorem. So if fz is analytic function at all points, we know what is analytic functions, and it is analytic at all points of a simply connected region in a complex plane, and if C is any closed curve within that region, then this closed integral C fz dz will be 0. So let's see what is the meaning of this actually. So let's see, this is our x and y axis, and this is a region. Outside this region, the function is not analytic, and it is analytic in this region only, and this is we are calling C. Okay. Now if it is analytic in all points, then take any contour inside this region. This fz dz on this contour will be 0, always 0. Okay. And when there is all points are analytic, at all points it is analytic, then we call this region as simply connected. Okay. When there is any point, any single point, when this is not analytic at that point, then it is called the multi-connected. Okay, multiply connected region. Like this means in this region, this particular r dash region is not analytic, then we call this as multiply connected region. But if at all points it is analytic, then we call it as simply connected region. Now if you take any contour and it will shrink down at any point inside it, then that point should be lying in this region, means it should be analytic. That point should be analytic for that function. Okay. Now see why it is not analytic here. See, if this r dash is non-analytic in this region, and you take a contour outside this, so it will shrink down to any point of this, then this function will not be analytic at that point. That's why this will not satisfy this condition. But if you take somewhere here, this will again collapse to this point, or this point, or this point, and these all are analytic points. So that's why this theorem will be valid. So just remember the difference, that what is simply connected region and what is multiply connected region. This fz any function is analytic in this r, and it is not analytic in this r dash, as I already told you. And I told you what is the difference between them, that these collapsing to an analytic point, these are collapsing to a non-analytic point. So this is multiply connected, this is simply connected, and this is our Cauchy integral theorem. So just take an example. Let's say we need to find fz is z square. So z square is analytic at all points in the complex plane because it is an entire function, I already told you. So at any point it will be analytic. So there is no, it's a simply connected region for this. So at every point this will be 0, means this value of this integral will be 0 by the Cauchy integral theorem, fz dz in any loop. So I hope this is clear to you. If you are still having any doubt regarding these reasons, you can put it in the comment section, or we will discuss more in the next lecture. Thank you everyone.